Welcome to this explainer. Today, we're unpacking a massive anomaly from the world of advanced mathematics. We're looking at how a mathematical framework can look perfectly stable on paper, yet mathematically explode into absolute chaos when actually put to the test. Specifically, we'll be diving into a fascinating comparative numerical simulation from the paper on the spectral bounds and trace class compactness of regulated summation functional frameworks. This paper presents an incredible clash between two mathematical models, and honestly, it reveals a whole lot about how numbers can sometimes deceive us. So, we're going to explore what the sources call the numerical stability paradox. Essentially, we'll uncover how an unregulated equation completely hides its fatal flaws by sitting inside a different, stabilized mathematical envelope. Think of it like a passenger in a high-speed car claiming they're running at 200 miles an hour on their own 2 feet, completely ignoring the vehicle that's actually carrying them. All right, let's look at our roadmap for this breakdown. First, the numerical stability paradox. Second, the Riemann zeta dataset. Third, the divergence trap. Fourth, our 5 extreme stress tests. And finally, the mathematical verdict. Part 1. The numerical stability paradox. Uncovering the mathematical illusion. The foundational building blocks of this impossible contradiction come down to a rigid contrast between two frameworks derived straight from our source material. On one side, we've got the standalone zero-pair interaction functional, or ZPIF. This framework attempts to introduce second-order quadratic interactions between spectral modes. Basically, it lets mathematical frequencies interact with each other. But crucially, as a standalone model, it's completely unregulated. It has absolutely no bounds. On the flip side, we have the scale-regulated aggregation framework, or SRA. The SRA acts as a mathematical governor. It applies what's called an AM-Regulator system's envelope to ensure stability. So the paradox we're investigating asks a simple question. What actually happens when you strip the SRA's regulatory bounds away from the ZPIF framework? Part 2. The Riemann zeta dataset, setting an unforgiving baseline. To find the truth between these two models, we need a neutral, universally recognized testing ground. So we use the non-trivial zeros of the Riemann zeta function. And the really crucial point here is that this dataset follows strict rules to ensure complete neutrality, totally free of any selective biases or floating point artifacts. The researchers didn't just pick random numbers. They used the L functions and modular forms database, the LMFDB, which is the global standard. They demanded sequential completeness, meaning you have to test the numbers in strict, unbroken chronological order, starting right from the fundamental ground state. Absolutely no cherry-picking allowed. Furthermore, the coordinates had to fall entirely within the proven bounds established by Turing-Platt verification protocols. We are talking about a certified error precision margin of plus or minus 2 to the power of negative 102. That is insane precision, and it guarantees that any explosion in the math is a structural failure of an equation itself, not just a rounding error on a computer. Part 3. The divergence trap. Revving the mathematical engine. Now, what happens when we treat our simulation like revving a car engine to 1,000,000 RPMs? When we push the truncation boundary to n equals 1,000,000, the unregulated math hits what's called the divergence trap, outlined as Theorem 1 in the source text. When evaluating an infinite summation of unregulated quadratic pairs, the math natively creates an immediate, catastrophic combinatorial explosion of energy. As that truncation bound expands to 1,000,000, the combinatorial energy of the standalone ZPIF explodes asymptotically to an infinite core horizon of 4.38 billion. It just completely flies off the handle, diverging straight to infinity. But look at this stark contrast. When the exact same dataset, those exact same Riemann zeta zeros, is governed by the SRA framework's AM-Regulator, the system is strictly trapped at a safe, bounded limit of 159.21. The regulator acts as a pre-stabilizing damping envelope. No matter how hard you push the truncation boundary, the SRA framework just absorbs the high-frequency energy and plateaus nicely at a stable mathematical horizon. Part 4. 5 extreme stress tests, mapping the chaos. To really understand why the unregulated math breaks the universe while the SRA survives, we need to run 5 extreme stress tests. We need to see exactly how the internal structure of the formula behaves under immense pressure. The results brilliantly illustrate the absolute failure of the unregulated model across 5 distinct dimensions. Look at the spectral density limit. That's our explosion to 4.38 billion versus the stable 159.21. But it gets so much worse for the standalone model. Look at Fisher information, which measures systemic entropy conservation. The ZPIF model collapses entirely to zero, meaning a total loss of internal structure, rendering the data unfalsifiable. The SRA rock solid at 2.146. Moving to the volatility profile, the standalone model hits infinity, causing a fatal variance collapse. The SRA is stably preserved at 0.413. Then we have trace norm preservation, which ensures quantum probability integrity. The standalone model is non-compact and infinite, whereas SRA is verified compact at 159.22. Finally, measuring Lyapunov stability, which is a gauge of how a system reacts to microscalar perturbations. The standalone ZPIF model rocks to positive infinity, meaning immediate catastrophic chaos. Meanwhile, the SRA manages a cool, asymptotically stable negative 0.142. And this data isn't just theoretical. Looking directly at the empirical evidence from the source paper's appendix, the standalone values completely diverge into infinity as the truncation bound expands. You can literally trace the rows as n grows, from 10 to 50 to 500 up to 1,000. By the time we hit 1,000, the standalone ZPIF is already at 2,277, while the SRI-regulated model is plateauing right around 158.95. By the time we project to infinity, the standalone column simply reads explosion and crash. So what does this mean in reality? Well, the physical and thermodynamic analogs in the stress test matrix confirm the verdict. When you push these mathematical models into thermodynamic analogs, an unregulated system suffers what physicists call an ultraviolet catastrophe. It experiences absolute thermal noise equilibrium and immediate chaotic collapse. Without the damping multiplier, these formulas are highly sensitive to noise and experience an absolute spectral collapse. They completely fail to map any stable, localized boundary layer. Part 5, the final mathematical verdict. The anatomy of the paradox resolved. So all of this begs a massive question. How did this catastrophically flawed standalone model ever appear stable in derivative works in the first place? How did anyone ever think this equation worked? Well, the paradox is solved by realizing the standalone ZPF equations were acting parasitically. According to the source analysis, these standalone models achieved stable convergence on paper only because they were inadvertently sheltered directly inside the envelope of the SRA framework. They were secretly borrowing the damping multipliers and pre-stabilized bounding constants of the SRA system's law to basically fake their convergence. Once you actually isolate the ZPF framework and divorce it from that SRA envelope, the math, predictably and violently, falls apart into chaotic divergence. This leaves us with a profound realization about the laws of operator theory, perfectly echoing the principles established by field medalists highlighted in our source text. Boundedness and compactness are non-negotiable conditions for operator validity. It's simple. You cannot just omit the mathematical guardrails, like the uniform regulation boundary, without entirely breaking the fundamental physics and mathematics of the system. Which really makes you wonder, right? If a major mathematical formula can hide its own explosive instability simply by hitching a ride inside a stronger framework, what other systems out there, in finance and engineering or in physics, are secretly relying on invisible guardrails just to survive? What's going to happen to our world when those guardrails are quietly removed and the system is pushed to 1,000,000 RPMs? Thank you so much for joining me on this explainer, and remember, always keep questioning the math behind the curtain.